the course will consist of 3 lectures, and I'll probably will try to make it quite introductory and self-contained, especially the first 2. Maybe in the 3rd lecture I will give some applications, and we'll kind of state maybe some open-ended problems. So I think already homework 1 is either posted or will be posted right away. And there will be certainly 2 homeworks. Maybe I will have also some kind of more advanced problems for the 3rd homework, which probably will not be graded, but I'll be happy to communicate about them privately. So the first homework will be due, I think, Wednesday, and so there will be 2 sessions on Tuesday and on Thursday, as Alexia was saying, with our TA, so Neela. So she is at the University of Utah, currently working with Dr. Rachel Skipper, also in geometric group theory, and also on groups generated by automata or self-similar groups. All right, so without further ado, let's start. So so I was thinking where to start, what would be the most appropriate place to start. And so maybe I decided to kind of make it start from motivational statement. So the motivational statement here, so again, so that's going to be just, I'm going to be writing on my screen. Here I prepared 1 paragraph. It's not going to be like that throughout the lecture, but I just wanted to have it prepared so that I save a little bit of time in the beginning. So we start with the Burnside problem. That was one of the main motivations for the study of these groups that we're talking about. And that goes back to 1902. So William Burnside said at that time, so of course people already worked with groups, which mostly came from topological perspective at that time and from Galois theory from the other end. So people did talk about them, but usually so for them, in most of the cases, groups were just some transformations, some symmetries of some space. And so he asked in 1902, a still undecided point in the theory of discontinuous groups is whether the group order of a group may be not finite, while the order of every operation it contains is finite. So if we translate it to modern terms, it will be stated like that. So that's what is known to be Burnside problem. So can a finitely generated group be infinite, while every element in the group has finite order? So that problem stayed open for 62 years until it was finally solved by Golod and Shafarevich. So let me just use the proper instrument. Okay, so the answer is yes. And first construction is Golod Shafarevich in 1964. Right. So I will not talk about these groups. So this is outside of the scope. Those are not self-similar groups. And so the somewhat minus of these groups is that it's a bit hard to work with them. So because it involves a certain infinite number of choices to define this group, and they're not quite constructive, even though, of course, you could study them from multiple perspectives. So this is also an interesting class of groups, but not within the scope of this course. So yeah, by the way, so whenever you have questions, just please let me know by either typing them in the chat, or you can just interrupt me. So I want to make it more interactive. Second, let me try to navigate with Zoom. Okay. Chat, so that I can see the chat. Okay. There we go. So now I think I see what's written in the chat. Okay, so as I said, the answer is yes, but the real motivation for study of self-similar group was a different answer, and so we're going to study this answer during this course. So that was a group called now Grigorchi group. So the easiest example comes from self-similar groups. So self-similar group called Grigorchi group. So this group was constructed, oops, not 18, but 1980 by Rostislav Grigorchuk. And so that basically sparkled the whole theory of self-similar groups. And so well, it has been studied very extensively since then. So let me start introducing this class. And so later on, it was discovered that this class answers not just this problem, Burnside problem, but also other problems. And maybe I'll talk about them a little bit in more details later. So, but specifically, for example, Milner problem on growth of groups. So this Grigorchi group happened to be also of intermediate growth. I'll talk a little bit in more details later about that. That also was the first example of a group which is amenable but non-elementary amenable. So where amenability, that's the property which stands behind Banach-Tarski paradox, probably that you probably have heard of. So that you can take a ball and cut it in finite number of pieces and rearrange these pieces using just motion in three-dimensional space and create two balls. So behind this Banach-Tarski paradox lies the group theoretic property of amenability. And so the reason that you could do that is because in three-dimensional space, so the group of all motions of three-dimensional space contains a free group. And so a free group is non-amenable, so that's why you could have this subdivision of a ball such that you could move pieces around and create two balls out of those. So this property also goes back to 1920s to von Neumann, and for a long time it was kind of an open question. So what are those amenable groups? It's still an open question in general. There are some groups like Thomson's group F, which we still don't know whether that's amenable or not. But the point was that people tried to classify those amenable groups, to characterize these classes in other terms. And for a long time, there were no examples of groups which are amenable, so that this decomposition called paradoxical decomposition is not possible, and such that they cannot be obtained from abelian groups, which are known to be non-amenable by certain easy constructions. And so Grigorchi group served as the first counterexample to that conjecture. So basically that was an amenable group, so you cannot do this Banach-Tarski decomposition with this group, but it cannot be built from abelian groups. Okay, then it served also as an example of a Atiyah conjecture. Maybe I'll just I'll mention that. So other conjectures answered with this group, right? So Milner problem on growth. Again, this is just introduction, so I will tell more about Milner problem a bit later. So then first example of amenable, but not elementary amenable. And so then there was another connection to Atiyah conjecture on L2 beta numbers. So that's related to the spectrum of various operators on the Kelly graphs of the groups. So connecting to analysis as well. Strong Atiyah conjecture on L2 beta numbers. And so quite soon, it was understood that this is a very interesting class with very unusual properties that people just haven't seen before. So there is no way to characterize the self-similar groups in some other ways often. So, for example, all of the self-similar groups will be defined by Mealy automata, and so this is the easiest way to define them. So there's no way to sometimes build this group from other groups, right? Okay, so let me start by maybe bringing up the object on which these groups will act. So even though historically that was not the way the Grigorchik group was constructed, Grigorchik group was constructed by Grigorchik as a subgroup of the transformations of a unit interval. But the most geometrically appealing and uh, beautiful, I would say, way to talk about them is by the action by automorphisms on rooted trees. Okay, so let's start with that. So rooted trees. So, well, of course, what's the tree? Tree is just connected graph without cycles, right? Uh, so I'm just setting up the terminology. Connected graph with no cycles. Now we say that the tree is rooted if we select one vertex. So a rooted tree, that's just a tree with selected vertex called a root. Called the root. Okay, so some of the trees are finite, but we're gonna study only infinite trees, specifically in the context of this group. So let's say definition. So regular DRE rooted tree is, well, maybe I'll just draw a picture. So you just, that's what you think it is, so that I will save time a little bit. So you have a root, right? And then every vertex then has a certain number of children. So this is a root, right? And then every child of this root is, again, the root of a new subtree, which is isomorphic to the big one, right? So you have every vertex has d children. Okay. So, and then it goes on up to infinity. So usually it's faster to draw it on the computer, but it's fine. Okay. So let me just write it, is a rooted tree in which every vertex, so I'll write has d children, and I have to tell, of course, what are children, but probably it's clear from the context. So if you know, so in a tree, there is always exactly one path from any vertex to the root, right? And then, so all the neighbors of a given vertex, which are not on that path, are called children. So that's what it is, in which every vertex has exactly the children. Okay, so it goes on to infinity, right? And that's going to be this rooted tree. And we're going to consider automorphisms of this tree, and more generally, we will even consider endomorphisms. So we're going to be considering maps from this graph to itself that preserves the adjacency relation, incidence relation. Okay, so self-similar groups act on these rooted trees by graph automorphisms. So of course, that's a rooted tree. So technically, an automorphism of a rooted tree must also preserve the root. But if we just look at that carefully here, we'll see that the root is the only vertex of degree d. So other vertices are of degree d plus 1 because they have d children and there is one parent, right? So that's why specifically for regular DRA trees, any automorphism of this tree will preserve the root even if we don't consider that as a rooted tree, right? So automorphisms, they will preserve the distances as well, right? So that means that any vertex of level 1, it will have to be mapped to some other vertex of level 1. every vertex of level 2 will be mapped to some other vertex of level 2, where levels are just all the vertices at a fixed distance from the root, right? So basically levels of the tree are spheres in this graph. And these levels are preserved under the action of any subgroup of an endomorphism group, right? So we naturally have kind of a partition of this tree into these subsets called levels of the tree. Okay, so now the question is, how do we characterize these automorphisms, right? So we have to come up with some language that will help us to talk about them and will help us to study these groups. And the first, we're gonna label the vertices of the tree in probably the most natural way. So I'm going to flip to the next page. Okay, so the tree itself, maybe I have to, well, maybe let me draw another one. So first we label the vertices of the tree with finite words over some finite alphabet x. So how to label vertices of a DRE tree. So let x be finite alphabet of cardinality d. Right? So for our purposes, for example, you could take x to be 0, 1, up to d minus 1. It really doesn't matter, but let's just say that this is our x. It might matter when we consider some examples of self-similar groups, in which case it is natural sometimes to put some algebraic structure on x or on x infinity, and then consider some transformations of some spaces that will induce automorphisms or endomorphisms of this tree. So, and let x star be the set of all finite words. Over x, right? Including, of course, the trivial word, the empty word, including the empty word, which will denote like an empty set. Okay, sometimes it's denoted lambda, sometimes it's denoted epsilon, but we're going to denote it by this symbol. Okay, so then x star, the set of all finite words, is naturally endowed with the structure of a DRE rooted tree. In the following way, so the root will correspond to the empty word, and then let's say that, well, in general, let's say this is equal to x1 up to xd, right? So this is our alphabet, right? So then the vertices of the first level are labeled by x1, x2, and so on xd, so by the words of length 1. The vertices of the second level are labeled by the words of length 2. So this is going to be x1, 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 x2, x1, xd, and so on. And the last one will be xd, x1, xd, xd, and so on. So every vertex of this tree will be labeled by some finite word over x. So this is x2, something, something, x I, where where I is just some index from 0 to d minus 1. All right, so once we set up the labeling of the vertices, we could now talk about automorphisms of this tree in a more precise way. We could say, for example, that we want to send vertex labeled by x1 to vertex labeled by x2, right? So this gives us some coordinate system in the tree. So that's all it is. So now so how do you describe these automorphisms? Well, there are several languages which are equivalent, and let me start with the one that comes from theory of automata, from basically formal language theory. So now I will introduce. So question is how to describe. Well, in general, I will describe actually endomorphisms, endo or automorphisms of the tree X star. Okay, that's the question that we're going to answer, right? So now we consider X star as a tree, right? And now I have to be here a little bit careful because, of course, X star. So for those of you who have looked into the theory of semigroups, of course, X star also is a monoid. You can multiply two words in X star just by concatenation. And then, of course, monoid is an algebraic structure, and you can consider endomorphisms and automorphisms of this monoid. So here I have to be very specific that we are not considering those automorphisms or endomorphisms. We are considering automorphisms and endomorphisms of this set viewed as a tree, right? So these are graph automorphisms and graph endomorphisms. Just don't do this mistake in your mind. So we're just talking about graphs. That's it. Okay, so let's start with way one. So we can use the language of Mealy automata. Okay, so what it is. So basically, this is the machine that sometimes it's called transducer as well, that will transduce finite words into finite words. And that's exactly what we need here, because if we want to define some automorphism of this tree, so that just means that we have to find the recipe or the algorithm, right? So that will tell us that this vertex, which is labeled by x1, x2, for example, has to move to vertex xd, x1. So what are those automata? So well, let me probably start with just an example, and then I'll give a formal definition. Okay. So let's do this example. So what is an automaton? An automaton is just a graph that has certain nodes which are labeled. Let's call this, for example, tau, and let's call this ID for some mysterious purposes. That will be clear in a second. Okay, and so these nodes are connected by edges. So basically, this is oriented graph, right? And so the edges are also labeled, and they are labeled by pairs of letters from X. Okay, so in this particular one, let's say that this is 0, 1, and let's say that this is 1, 0, and this is 0, 0, and let's just try another one, 1, 1. Okay. So I will not allow at this time any labelings. So there will be certain restrictions on the set of labelings so that we either get endomorphisms or automorphisms, and those restrictions will be very natural. So how does this machine work on the tree? So once you fix a state that's going to be called initial automaton, let's say that we fix the state here, tau. Okay, so then it will read the input word and it will output some word as well in the following way. So suppose you have some word, I don't know. So you have a word, yeah, maybe I have to move this example to the next page so that it's going to be a little bit easier to read. Of course, I will pause the slides after that. So let me take this to the next slide. Okay. So this is our automaton. Whatever it is, we'll give a formal definition just in a second. So here just the example to build intuition. So, and suppose you have some input word. So automata will define transformations from X star to X star, right? So finite words to finite words that will turn out to be endomorphisms or automorphisms depending on the property of this automata, right? So an example will be like that. So suppose that you start from input word. Let's say that you read 0, 0, 0. Well, maybe let me just sparse them a little bit. It's 0, 0, let's say 1, 0, 1. Okay, and this is the input word. And suppose that you are in, you start with the state tau. So this is input, these are states, and this is output. Okay, so disappeared. Just 1 second. Probably I just switched to the next page by mistake. Okay, yeah, there we go. Okay, so you are in state tau and you read letter 0. That's the first letter 0, right? So what you do is the following. So you look at your state, right? And you look at the arrow such that the label of this arrow, well, it's a pair of letters from X. So the first component is your input letter. So basically it tells that if you read the letter 0 while you are in state tau, you will output letter 1, and then you move back to state tau, because that's where the endpoint of this arrow is, right? So this is what we do. So we flip 0 to 1, right? And then we move tau to tau again, right? Because that's the new state, which such that the automaton kind of shifted to this new state. And now we process the rest of the word exactly in the same way. So we read 1 more 0, so we repeat what we've done. So we look for the arrow labeled by 0 in the first component, and then we output the second component of that label. So, and again, that's the same arrow as before. So we output 1, and then we go back to state tau. So now we read 1, right? So that means that we look now for this arrow over here, because this arrow is labeled by a pair whose first component is 1. And then we output 0, right? So, and then we go to the new state, which is labeled as ID, right? So it's going to be called ID. Now it's clear why it's called ID, because now whatever you read, if you read 0, you output 0, and you go back to the same state. And if you read 1, you output 1, and you go back to the same state, right? So then, and then you repeat, right? So no matter what you read after that, it will not change the input characters, right? So that's why you have that 0 is transformed to 0, and you go to state ID, and then 1 is transformed to 1, and you go to state ID, right? So if you fix the initial state, and let's say that this is an automaton A, right? Then the automaton with initial state is called initial automaton, let's say tau. And then, so we're going to say that a tau will act on 0, 0, 1, 0, 1 as 1, 1, 0, 0, 1. Right. So that's how automata transform input words into the output words. That's the idea. Now with this idea, so yeah, by the way, any questions so far? Okay, so I hope that everything is clear so far. Now,
just one question about degree of transitivity of endomorphism group. Is it 1 or more than 1?
Well, so that depends on what set you're talking about, right? Because of course the levels are preserved, right? So you cannot move vertices from level 2 to level 5, for example, right? So that's why there is no transitivity at all on the full set of X star, right? But within the levels, of course, the degree of transitivity, it's just going to be, well, we'll get to that, but so you can definitely move any point to any point. So degree of transitivity will be definitely 1. But for pairs, you cannot move any pair to any other pair, right? Because that will depend where this pair. So if you have a pair of points on some level, right? So then that means that there are passes from the root of the tree to these vertices, and these passes will diverge at some level, right? And so then if you have one pair that diverges at level 5, for example, and then you have another pair that diverges at level 4, then there is no way to move first pair into the second pair, right? So
Yes,
that's why
yes.
you can, yeah. So basically it's going to be 1 if you restrict yourself to the levels, and it's going to be 0 if you consider the full set.
Thank you.
Okay, so so this is how it works informally. Now let's give a formal definition. So what is an automaton? So a Milli automaton or transducer. And again, so right now I'm just defining a language to work with these automorphisms, and I'm going to get to self-similar groups just in a second, but this is just one of the equivalent languages. So is a four-tuple uh, A, which is Q, X, and let's say delta and lambda. So what are those guys? So this is set of states. I don't want to require that this set of states is finite at this time, because we're going to actually work with infinite automata as well. So X is going to be our finite alphabet. So in this case, set of states, for example, is just made of two elements, which are labeled by tau and id. Okay. Now, delta and lambda, those are transition and output functions. Transition function will tell you where you go in your automaton if you read an input letter. And output function will tell you what letter you output when you are somewhere in the automaton, and then you read some input letter. So let's start with lambda, for example, right? So this is output function. So it's from Q cross X. You read state and a letter, and you output letter to X. And so delta is going to be the transition function. And so that's going to be from Q cross X to Q. So you read, you are in state Q, and you read the letter X, and then it tells you where to go inside the automaton. Okay, so this is what is a Milli automaton. And then just a continuation of this definition. So an initial Milli automaton, so let's just move it a little bit up. Oops, Milli automaton is a five-tuple. So just in addition to this tuple from a non-initial automaton, you also add one more component, which is just initial state. So let's say AQ, which is Q, X, delta, lambda, as before, and then little q, where this q is in Q. So this is the state from which you start from. Of course, Q is not a set of rational numbers, that's a set of states. All right, so now that's the formal definition, right? And so now we have to define how this initial automaton acts on our rooted tree. And so maybe let's just move to the next page. Okay. So maybe let me just copy this definition so that we can look at that on the next page as well. Okay. Okay. So that's our definition. Now the point is that each initial Mealy automaton defines a graph endomorphism of X star, right? Viewed as a tree, right? So we have to teach how this initial automaton will act on any input word, right? So we've seen the example, so we're just formalizing our example essentially, right? So we can extend lambda. So remember, lambda was the output function from q cross x to x, right? So we can extend lambda to a different function, which we also denote by lambda, from q cross x star to x star, right? So here you start at a state, right? And then you read some finite word, and then you output this finite word, right? And let's say delta and lambda, because you could extend both of them, right? So lambda, well, let's be a little bit more precise. So lambda will be from q cross x star to x star, and delta from q cross x star to q. Okay, so now you're allowed to read finite words. The output will be finite word, and if you are in state q and you read finite word, you will end up in some other state of this automaton. Okay, so in what way? In the most natural way, if you have, for example, delta, you were in state S and you read x1, x2, x3, and so on, xn, right? You define it recursively. So just the procedure that I described, right? So you were in state S, right? Let's be draw a picture. So you were in state S, right? And then you read, you find the arrow labeled by x1, right? And then you output, of course, lambda of sx1, and you go to delta of sx1. Okay, and then you process the rest of the word with this state. So that's just right formula what that means. So we apply delta, right, at the state delta of s comma x1 at this new states where we arrived, and we apply this delta to a word which is shorter, x2, x3, and so on, xn, to the rest of the word. So this is recurrent definition, and that's up until this word becomes of length 1, in which case delta is just regular delta from the definition. And similarly, you define lambda of s, x1, x2. So this is a transition function, right? X3 and so on, xn. So for lambda, that's going to be the output function. So remember what we've done. So when we read x1, we output lambda of sx1, and then we process the rest of the word with this state, right? So that's why here we should write lambda of s comma x1. That's the first output letter, and then the rest of the word will be just the lambda of, now we apply, we are in a new state, which is delta of s x1, and we apply to x2, x3, and so on, xn. Okay, so this is the formal extension, right? And now, of course, once you fix a state, right? So given a state q in q, we define lambda q of, let's say lambda q will be just a function from x star to x star, and that's going to be our transformation that we are looking for, from x star to x star by lambda q of x1, xn to be just lambda of q x1, xn. Okay. So when we fix the first component, right, we're just gonna get a function of one argument, which is a finite word, right? And so this is exactly the action of the initial automaton AQ on X star. Okay. So any questions? Okay. So let's move then. So there is a homework problem that probably I will not go over right now and let you think about that. So I'll just write that as proposition. Uh, so or exercise probably. Uh, given an initial automaton, AQ, right, which is QX delta lambda Q, right? The transformation lambda Q from X star to X star that we just defined above is, well, let's say not is, but induces an endomorphism of the tree X star, graph endomorphism. Let's say a graph endomorphism. All right, so, well, it's kind of natural. The idea is very simple, right? Because if you have, for example, let's talk about binary tree, right? So this is, let's say, let's say this is 0, this is 1, this is 0, 0, 0, 1, 1, 0, 1, 1, and so on. 0, 0, 0, and 1, 1, 1 at the end. So if you had, for example, that two vertices were adjacent, right? So this one and this one. So let's say that these were adjacent, right? That means that this is 0, 1, and then this will be 0, 1, 0, right? So you get the child from the parent by appending one letter at the end, right? And then if you start acting on this string or on this string by this transformation lambda q by an automaton, right? You first process the beginning, and then you, after you process the beginning, so maybe, for example, maybe, so this vertex went to this vertex here, for example. Let's do this black, and so this one will be okay. So say 0, 1 went to 1, 1. But then you act on this last letter 0 in the same way, right? So you already know that 0, 1 is mapped to 1, 1. And then maybe the 0 will be mapped either to 0 or to 1. And accordingly, this vertex will be mapped either here or here. Right, one of these two. Right, so of course there is a formal proof by induction, and I'll leave this proof for you. It's not a complicated proof. The idea is very simple. That's just because we act on the words letter by letter. All right, so of course we are here to talk about groups. So then a natural question is when these endomorphisms will actually be automorphisms. So when we can permute the levels of the tree. And so for that, we have, of course, to define what does it mean to be invertible automaton. Okay, so definition. So it's kind of natural what you want to get. So, for example, if you have a state Q, right, and then you have a bunch of arrows, right, you have to have, by definition, you have to have exactly one arrow for every input letter. So, for example, 0 goes to it's going to be lambda of q0, and then 1 will go to lambda of q1, and so on. Maybe d minus 1 will go to lambda of q d minus 1. Right, it will go to state here, state here, state here. Some of these states might be the same, right? So if you want this transformation to be invertible, at least you want to have that this lambda will define a permutation of the input letters, right? So for example, if you have that if you read 0, you go to 0, right? And if you read 1, you also go to 0, right? So this is something that will not define an automorphism, not invertible. Yeah, it was supposed to be red, but I think it's fine if it's green. So it's not invertible because if you want to invert, you will want to flip these arrows, these labels, and you will transform back 0 to the input letter 0. But here you don't know where to transform it, either to 0 or to 1, right? So this is not invertible. In order to be invertible, you want to see the permutation at every vertex, at every node of the automata. Okay. So definition. So an automaton is invertible. So if for every q in q, we have that lambda q. Now I'm going to restrict it to q, sorry, not q, but x. To x is a bijection, then a q, in our case, is called invertible. Okay, and then again, proposition. Each invertible automaton initial Miller automaton. Yeah, let's just maybe do it a little bit more proper, in a proper way. So each invertible initial Miller automaton defines an automorphism of X star. Okay, so this is where we get to finally to the groups, right? So now I can state the definition. What is a group, which is either automaton group or self-similar group? Okay, so definition. So given a non-initial automaton, let's call it A, which is Qx delta lambda. So we don't restrict ourselves to finite sets of states at this time. So the automaton, I'll write semi so that I will have two definitions at once, two definitions at one. Semi group, let's say S of A or G of A, depending on whether you're invertible or not invertible. And let's say here I want to add invertible in, well, yeah, let's just, because, yeah, I wanted to add invertible, but invertible correspond to groups, not to semi-groups. Right, so let's just write it as is. So the automaton semigroup, S of A or G of A, or which is a different name for self-similar semigroup, is group either is either S of A, semigroup generated by AQ from X star to X star with operation of composition of these transformations, or G of A, which is the same thing, but now it's considered as a group, where operation is composition. Okay, so this is the main definition for us. So automaton group, maybe let me just highlight it somehow. Yellow. Okay. Okay, so, and I'll just write down, so another definition, another term, it's called self-similar semi-or group. Self-similar semi-group. So we're going to be talking mostly about groups, but in general, you have semi-groups because those transformations of X star, they might not be invertible, but you still can consider compositions of those. In that case, you're going to have a semi-group, but if those transformations are invertible, then you have a group. All right, so let's do, we don't have too much time. We started a few minutes later, so let me just do a couple of examples, very small examples. So baby example. Let's just take, for example, a group generated by one state automaton. Let's say, call it A, and let's say that 0 goes to 1. And then, so instead of drawing two arrows, I will just use the same arrow and say that 1 goes to 0. Right? So let's call this A. Okay. So it's just one state, right? And two letters. So here Q is equal to A, X is equal to 0, 1, right? And lambda, let's say delta, right? Delta and lambda are defined from this diagram. So let's try to understand what this automaton does. So if you start acting, right, by A on any input string, so let's see, 1, 0, 1, 1, 0, and so on, right? I have to sparse them a little bit. 0, 1, 1, and so on, right? So you were in A, you read 1, you flip it to 0 because you flip 1 to 0 and 0 to 1, and then you move to the same state A, right? And then you move on, you just flip every single input letter. 0 goes to 1, and then 1 goes to 0, you go back to A, and 1 goes to 0, and so on. So every letter is flipped. Then guess what happens if you apply it again, right? So if you apply it again, of course, 0 will be flipped to 1, and you go back to state A. 1 will be flipped to 0, and you go back to state A, and same as before, 0 is flipped to 1, and then 0 is flipped to 1 again. So you get back to the same word, right? So this is the same word, which means that if you apply this transformation twice, you're going to get the identity, and which means that the group just has order 2. So we have that AA squared is equal to identity. And by definition, the group is generated by all the states. There is one state. So G of A will be just isomorphic to Z mod 2Z. That's the simplest baby example, aside the trivial example in which we don't flip 0 and 1, in which case we would get a trivial group of groups. Okay, so that's a baby example. Right, so far, nothing really new. So let's do a toddler example, and then I will finish with adult example after that. Okay. Toddler example. That's the one that we started from. So let's say we have automaton with two states, tau and ID, right? And if you read 0, you output 1. If you read 1, you output 0, and then you go to the identity state, which does nothing. 0 goes to 0, 1 goes to 1. Let's try to apply. So of course, this is the identity state. So this defines identity transformation. Right, so that's why the group generated by this automaton, this is our new A. Of course, it will be just generated by, let me just write tau, and that will be just a short form for a tau. So just instead of writing a tau, I will be just writing tau, right? The question is whether this group is finite or not. So of course it's a cyclic group. It either could be Z mod n Z for some n, or it could be just Z. Okay. Well, let's see what happens. So you start with an A with tau, and let's say that you have some input word 0, 0, 0, 0, 0, right? And you have tau. Okay, so you flip 0 to 1, right? And then you go to tau. Sorry, I think I made it wrong. So if it's 1, you flip to 0, and if it's 0, you flip to 1. My apologies. If it's 1, you flip to 0, and if it's 0, you flip to 1, and then you do nothing after that, right? So, and then you go to identity, and then nothing happens, right? So you have 0, 0, 0, 0, right? Yeah, let me move this example maybe to the next page, so that's going to be a little bit easier. So sorry for being a little bit over time, but I will be done quite fast. Okay, so copy, and then just paste it here. Okay. So now we apply tau again because we want to see whether we get back to the same thing or not ever, right? So now once we apply 1, right, we map it to 0, and then we go back to tau, right? So that's 0 and then tau. And then we see, you see that we process exactly in the same way as before, right? Because now tau reads 0, 0, 0, 0, and that's what we've done before. So we know what will happen. So it's going to be 1, 0, 0, 0, and so on. Well, so it's definitely different from the first two. So now we apply tau again. 0 is transformed to 1, and we move to identity right away. And then identity doesn't do anything, so it's going to be 1, 1, 0, 0, and so on. If we apply tau again, right, so then 1 will be transformed to 0, and we go to tau. Tau is transformed, 1 is transformed to 0, and you go back to tau. And then we know what to do. All right, so it's going to go to 1, 0, 0, and so on. So if we see what's going on, you probably can notice the pattern, right? Because we're just adding 1 in dyadic integers, right? So with the carryover, right? So that's just a binary expansions of all integers, right? 1, this is 0, 1, 1, 1, 0, 0, 1, and so on. And basically, this automaton is just the algorithm how we add with the carryover. So as long as we are reading 1, we flip it to 0, and we remember carryover. But once we read 0, we flip it to 1, and then there is no carryover, so we don't do anything else after that. Right? So that's why once we move on, it will never get back to 0, 0, 0. So tau has infinite order, and the group generated by this automaton will be just isomorphic to Z, infinite cyclic group. Okay, it's a little bit harder to show that it's infinite, so we're talking about the order of an element. So finally, let me just introduce you to adult example. I hope that everyone is at least 18 in this chat. So adult example, that will be Grigorchi group. And we'll probably try to prove next time that it's actually infinite periodic group. And so the group is defined as follows. It has 5 states. Okay, so now this is going to be A. Sorry, not. Yeah, that this is going to be A. This is going to be identity. Our old friend, 0 goes to 1, 0 goes to 0, 1 goes to 1. A will be not exactly our old friend, but also very simple. So 0 goes to 1, 1 goes to 0, right? So it flips 0 to 1, 1 goes to 0, but then it doesn't do anything with the rest. And then you have a cycle, BCD. Okay, so if you are in B and you read 0, you go to A, 0, and then you don't change any input letters here. If you read 1, you go to C. So 1 goes to 1. If you're in C, you read 0, you go to A, 0 goes to 0, and if you read 1, you go to D. 1 goes to 1. And finally, if you are in D, you read 0, you go to identity, initial point. So 0 goes to 0, and then if you read 1, you go to B, 1 goes to 1. So there is a cycle here labeled by ones as input letters, right? And then if you read 0 at B and C, you go to the state A that flips the initial letter. That's the only active state that flips the initial letter, the input letter. All other states don't flip the input letter. And then if you're in D and you read 0, you go to the identity right away. Okay, so that's the main example for this course, and we'll study this group next time. And probably I'm a little bit over time here, so I'll thank. I will thank everyone for attention, and maybe so in the homework, maybe I will just note that some of the problems might be moved to the second problem set because I think I didn't cover yet with recursion, which was important for some of the problems. But I'll make a comment on that in my email. Okay, so thank you everyone, and so let me just adjourn here. And let me know if you have questions, of course.
Excuse me, I have a question.
Yes, Maxim.
So regarding all this construction, so we define, we induce endomorphisms, sometimes automorphisms of a tree exactly, well, due to our construction. But is it possible to do something like this for general graphs? Say, I'm particularly interested in hypercubes, but like maybe in general, in overall. So, would it be possible to define some kind of structure of, like words where we have like some more connections in some sense? You see what I mean?
Well, maybe, I mean, specifically for hypercubes, probably you're talking mostly about coding theory, for example, if you're talking about applications, right? So I mean, of course, vertices of hypercubes also could be labeled by words of length, of a specific length. So you could consider those hypercubes, for example, as levels of some tree that is growing. So yeah. And so there is a construction called Schreier graphs, and so we're gonna talk about that next time. So it's not necessarily that you're gonna get hypercubes in that construction, but you could think of this set of hypercubes as a family of graphs which are naturally kind of fall in the structure of a rooted tree as well. Right, and then so like you do, for example, coding theory on the hypercubes, where you have the Hammond distance is basically the distance between 2 points in the hypercube. You could define similar codes on these graphs that appear from the action of these groups acting on rooted trees, right? So you also have the sequence of graphs. Those will not be hypercubes. And so, for example, one of the applications that I hope to get to will be Hanoi Towers group, in which those graphs that you see are larger and larger pieces of Sierpinski gaskets. And also you could run some coding theory on those graphs instead. Right. Of course, you could consider automorphism groups of these hypercubes as well, but I mean, this is probably there's no direct relation to these so similar groups here.
Okay, thank you so much.
May I ask about how to define, how to find the number of states of automaton having automorphism of rooted tree, and how we defined minimal number of states of an automaton whose function of
Mm-hmm.
translation function will isomorphic to this group.
Well, in general, so if you have any automaton, right? So I didn't get there yet, so we just defined the class of automaton or self-similar groups. You can solve the word problem in this class. So basically, if you have any word in generators, there is an algorithm that tells whether this word corresponds to a trivial element or not. And so when you, for example, try to, given some automorphism or endomorphism, you want to construct an automaton. And so that will be one of the homework problems as well. So here I just defined that every automaton will define endomorphism or automorphism. But actually, the opposite direction also works. If you have any endomorphism or automorphism of the tree, you can define an automaton that induces this automorphism or endomorphism. That's one of the homework problems. Well, then, if you start with endomorphism, right? So you want to understand what is the automaton, you just build it using this construction, and then you use the word problem algorithm to see which states are different, which states are the same, and that will give you the number of states for the specific automaton defining this endomorphism. But of course, this number of states could be infinite as well, in which case you might run into some problems because we have only finite amount of time, of course. But if you know, because of some other reasons, that the number of sections, the number of states of this endomorphism is finite, then it's quite easy to write down the automaton and to minimize it to make sure that every two states are actually different.
There is no standard algorithm to minimize
There
it.
is a standard algorithm to solve the word problem, and you apply this algorithm to distinguish two different states. And that's basically equivalent to minimization of automata.
Thank you. And who's find minimal generated system for a group of automorphism of regular tree? In which work we can read it if it's
if you take the full group of automorphisms, then it's actually will not be finitely generated, even topologically. So there will be no way to have the finite set of relations.
Restricted tree.
Once again?
For restricted tree, I'm sorry, I'm interested for finite number of levels.
For finite number of levels, well, then if you consider the full group, that's going to be the iterated Ritz product of the symmetric group, if you consider the full automorphism. And so I don't have that on the top of my head. So what will be the paper that contains the minimal generating set for this one? But I'm quite sure that has been studied. So basically, we're talking about minimal generating set for the Ritz product. And I will talk about Ritz products next time when we talk about different language to work with these groups. Right. Minimal generating set for the Ritz product of certain number of copies of symmetric group. Yeah, I don't have the answer right now, but probably I can try to look it up.
Oh, thank you. It would be interesting.
Okay. Some more questions? All right, so probably then I will just, I guess, finish this lecture. And so I'll see you all in 2 days. And so probably try to come tomorrow to recitation with Nilam. So you'll go mostly about homework problems. And I think that most of them you could solve now. The only thing that I didn't touch is the language of Ritz recursion, but I think the notes are posted, so you could look through the notes. It's just a different language to talk about the same data. And for the homework problems, once you understand the translation, it's very easy to, basically to solve most of these problems. Right, but formally I will introduce it on Wednesday, but feel free to read a little bit in advance.
Well, thank you.